Okay, let's look at this first one. We want to find the y-intercept. Now remember, always to find the y-intercept, you're going to just replace the x with 0. So what we have then is we have 0 minus 1 minus 9, and that's going to be negative 1 squared minus 9, which is 1 minus 9, which is negative 8. So we have a y-intercept of 0, negative 8. So that's how we find the y-intercept. Now next, we want to find the x-intercepts. So I take the entire function and set it equal to 0. So what we're doing is we're letting y be 0. To find the y-intercept, we let x be 0. To find the x-intercepts, we let y be 0. Okay. Now this type of equation, this type of second degree equation where we just have one little clump squared and then a number, whenever we have a situation like that, probably the easiest way to solve this is just use this um, square root property. You know, bring the 9 over to the other side in this case, and then square root both sides. So if I do that, we have x minus 1 equals plus or minus 3, the square root of 9. So we get our two x-intercepts. It's going to be negative, well, I bring the 1 over first, right? So I've got x equals 1 plus or minus 3. So here's what we have. We have 1 minus 3, comma 0, and 1 plus 3, comma 0. And these two are x-intercepts. So we have a root at 1 plus 3 and 1 minus 3. Now, as far as the vertex, this thing is in vertex form. So what we want to do is we know that we have an x-coordinate and a y-coordinate of our vertex. We get the x-coordinate from the parentheses with the x, only the opposite. So x minus 1, we have an x-coordinate of 1. The y-coordinate we get from the end. Because remember, this is of the form y equals a x minus h squared plus k, and our vertex is hk. Okay, let's look at this one then. We've got a little bit different form. Still, it's a second degree polynomial, but we still find the y-intercept the same way. We just take a 0 and put it in for x. So we've got g of 0, which is going to be 8. So we've got this point 0, 8. That's where the function crosses the y-axis. Now, as far as the x-intercepts, we take the function, just like before, and set it equal to 0. This is a little bit different form, though. What we're not going to do is bring the 8 over to the other side and then square root. That won't work this time because of this 6x here. So what we have is an option here. We can either try to solve this by factoring and use the zero product property, or we can use the quadratic formula. Sometimes the factoring is so straightforward, you don't want to, that's the easier way to do it. Like in this case, if I factor this, I could factor it pretty easily. X plus 4, x plus 2 equals 0. See, the 4 and 2 add up to 6 and multiply to give me 8. So immediately I find that x equals negative 4 or x equals negative 2. So this works when we have two things that are multiplied to give me 0. If two things multiplied together give you 0, then one of them needs to be 0 for that to be true. And that can happen if either x equals negative 4 or x equals negative 2. Now, if this were x plus 4 times x plus 2 equals some number like 5, we couldn't do this. But here's the thing. We have two X-intercepts, -4, 0, and we have -2, 0. Okay, x equals -4, x equals -2. Those are zeros of the function, and the intercepts would be -4, 0, and -2, 0. Now, as far as the vertex, well, the vertex is not of the form that what I'm calling the vertex form. I can't just look at that and tell what the x and the y coordinates are. So this is the case where we need to complete the square. So I'm going to group my x's together. Okay. So I group my x's together. I'm going to take half of the 6 and square it and add over here. Now, if I add a 9 inside the parentheses, I need to add a 9. I need to subtract a 9 to the outside to keep everything balanced. See, I added a 9 in there, and I can't just willy-nilly do that. I have to keep everything balanced, so I subtract off a 9. Now, really, I've done nothing. It's like I've added a 0. However, I've made it where I can rewrite this side over here by x plus 3 squared. In other words, this thing right here factors into this minus 1. See? So now I get a vertex of -3, -1. There it is. And that, because now I've got it in a vertex form. So what we want to do with these next two problems is find the y-intercept, the zeros, and the extreme left and right behavior. And then we just want to do a really rough sketch. Okay, so here's what we have. We want to find the y-intercept. Now there's always just going to be one of those. And we always find it just like with the second degree. We find it by letting x be 0 and then just do the computations here. See? So it looks like that's going to be -8. So we have a y-intercept of 0, -8. That's where it crosses the y-axis. Now, for the zeros, the x-intercepts, we're going to set this whole thing equal to 0. So to find the zeros, we set the whole function equal to 0. So we've got x minus 1 times x plus 2 times x plus 4 equal to 0. And once again, we use the zero product property. So our zeros are x equals 1, x equals -2, x equals -4. These are the zeros. These are the values that if we plug that into the f of x, we get 0. Now, each one of them has a multiplicity of 1. Notice each one of these was raised to the first power. So we have a multiplicity of 1. Now, as far as the extreme left and right behavior, remember what we said about the extreme left and right behavior. We said when you have a polynomial, sometimes the leading coefficient will be positive and sometimes the leading coefficient will be negative. Sometimes the power of the function of the polynomial will be even and sometimes it will be odd. We use this information to determine the extreme left and right behavior. In other words, what the polynomial does way out toward positive infinity and way out toward negative infinity. If you have an even polynomial and the leading coefficient is even, it behaves like x squared, up to the left and up to the right. If you have that same even polynomial, but the leading coefficient is negative, then it flips it down to the left and down to the right. Now, as far as if you have an odd power, a positive leading coefficient, it's down to the left and up to the right, like the cube, x cubed. And if you put a negative in front, it flips it. So we can use that table to determine the extreme left and right behavior here. Now this particular one, we've got a 1 degree there, another degree. If we multiply those, we get a second degree. And then if we multiply by this one, we get the third degree. So this is a third degree polynomial, so it's going to behave like this, down to the left, up to the right. Now I'm just going to do a quick rough sketch. That's all we're trying to do here. It crosses down here at 0, -8. It also crosses at -2, -4, and at 1. It has, if I go to the leftmost 0, I can see it's finally going to go down to the left. If I go to the right over here, it goes up to the right. Now I just sketch through, starting at one of those end roots there and then just sketching through. This is a really rough sketch of the behavior of this polynomial. Okay, so this one is just like, part A. It's just like f of x, except we notice that we've got a square up here on this for this 0, for this factor here. So let's see how we would proceed. First of all, the y-intercept. Same old situation. We just put a 0 in for x, and we multiply, do the arithmetic. So this would be 2. So we've got the y-intercept of 0, 2. Now, as far as the zeros go, from this one we've got x equals 2. From this one we've got x equals 1. And from this one we've got x equals -1. But notice this thing right here. I'm going to put a double line under that to indicate that has multiplicity of 2. These ones, this and this, have multiplicity 1. Okay? So this is going to be important when I sketch the graph. Now, as far as the extreme left and right behavior goes, we've got a power of 2 here, a power of 1 here, and a power of 1 here. So when these two are multiplied together, these ones, I get a square. When I multiply this out, I get a square. So when I multiply it all together, I get a 4th power. So look, 2, 3, 4. I can just count that. 2, 3, 4. I'm going to get a 4th power. That means the extreme left and right behavior is like that. Up to the left, up to the right. So now I'm ready to, do a really rough sketch. We've got 1, 2, -1, and then 0, 2 here. It goes up and up. And I have to remember at -1, it's going to bounce. See? So getting ready to sketch. There's our rough sketch. Okay, so now we're going the other way. We've taken a polynomial and found, a rough sketch. Now we want to go the other way. We're given the information. We're given the intercepts, and now we want to see if we can write an equation. Well, here we go. So we've got p of x equals, let's see here, x plus 6, x plus 3, x minus 2, and x minus 5. See? So that's a root, so we know a factor is x minus that. So that's where we got it. -3 is a root, so x plus 3 is a factor. It's going to be the opposite. Now, this polynomial right here is a polynomial that has these roots, these x-intercepts. But that's not good enough. I want it also to have this y-intercept. So I'm going to put an a in front, and I'm going to find an a that will make that polynomial graph pass through the y-intercept of 0, 10. So here's what I do. I put a 10 here for p of x, a 0 in for the x. I just zero out all those x's. And now I want to solve for a. Well, I could multiply all of this out and divide, but notice I've got a -2 times a -5. That's a positive 10. Let me just divide that out on both sides. So I get a 1 over here. So what I find is that a is equal to 1 over 18. See, because I just divided by this 18. So that's my polynomial. Now for this one here, okay, for this one, I take the same path. I'm going to have a times x minus 1, but it bounces there, right? So it has an even multiplicity. So I put a 2 and then an x minus 3. There's my polynomial on that one. Now, I need to figure out what a is, and I'm told that this is 0, 9, so I've got 9 equals a times negative 1 squared times negative 3. Whoops. Get the eraser. Okay. So it looks like that's going to be a positive, or negative 3. So a, if we work this out, a is equal to negative 3, it looks like, right? Because this whole side over here is negative 3, and when I divide 9 by negative 3, I get negative 3. Okay, so now here's what we want to do. We want to find the other zeros for a polynomial if we're given one or more of the zeros. So in this first case here, I'm given x cubed plus 4x squared plus x minus 6, and I'm told that x equals 1 is a 0. So you need to find the other zeros. Okay, so here's what we have. We're told that x equals 1 is a 0. That immediately means that x minus 1 is a factor. Now, if I've got a factor and I want to find the other factors, I just divide. So if I know 2 is a factor of 6, I can divide 2 into 6 and find 3, another factor. So I'm going to divide x minus 3 into the function. Now, if indeed x equals 1 is a 0, then I should get 0 remainder here. I shouldn't get any remainder. So I start dividing. I've got x into x cubed, that goes x squared. And then I multiply. Okay, there we go. And then I subtract, so that's going to be 5x squared. Now I divide x into 5x squared, and I get 5x, 5x. Oh yeah, I need to bring down the x, I guess, here, don't I? Okay. So now I multiply 5x times x minus 1. Let me give myself some more room here. Hang on. I didn't plan ahead. Let me just bring this next problem down a bit. There, fixed it. Okay. Okay, so let's see what we've got now. Okay, so I'm going to multiply 5x times x minus 1. I get 5x squared minus 5x. And I subtract, and I get 6x. Bring down the minus 6. And then x will go into 6x 6 times. And then multiply 6x minus 6. And of course, I get 0 remainder, which is a good thing, because if we found a remainder, it would mean that, yeah, x equals 1 is not a 0. So here's what we have. We have x minus 1 times x squared plus 5x plus 6. This is that polynomial factored partly. But I notice that this here will factor a little more. So what I've got is x minus 1 times x plus 2 times x plus 3. There it goes. Yeah. So it looks like our zeros are 1, negative 2, negative 3. These are the zeros. Okay. Now let's look at this one. We want to find the zeros of g of x, given that x equals 3i is a 0. Now remember this, that if x equals 3i is a 0, then x equals negative 3i is also a 0, because these zeros in complex numbers travel in conjugate pairs. The imaginary roots, these non-real roots, travel in conjugate pairs. So 3i is a root. That means that negative 3i is also a root. Okay, now we start by doing this. I say, okay, x plus 3i is a root, then x minus 3i or x equals 3i is a root, then x minus 3i is a factor. And likewise, x plus 3i is a factor because 3i and negative 3i are both roots. Now let me multiply this out, and I get x squared plus 9. You go through and multiply it all out. This is what I need to divide into this big thing here. So let's take a look and see how that's going to be. We've got x squared plus 0x plus 9. I put the 0x just as a placeholder, so to keep everything lined up as I go through. So I got x to the fourth plus 7x cubed plus 19x squared. So this is a big one here. Okay, let's see now. Let's see how this turns out. I'm going to take x into x to the fourth. That's going to be x squared times, and then I multiply. So I get x squared times x squared, that's x to the fourth, plus 0x cubed plus 9x squared. Yeah, see, now I've got everything lined up. And if I subtract, I'm going to get 7x cubed plus 10x squared. Let me go ahead and bring down this 63x. So I just brought this down. Okay, now I'm going to divide x squared into 7x cubed, and that's going to give me 7x. Okay, now let's see what I've got here. I've got 7x cubed plus 0x squared plus 63x. Here we go. Now if I subtract, I'm going to get 10x squared, and 63 minus 63, that's 0. So then I bring down the 90. Okay. Now, x squared will go into 10x squared, that's 10. Then I multiply, and you can see that I get 0 remainder. So here are my, here's what I've got. I've got x minus, what was it, 3i, x minus, whoops. Let me go down here a little bit. I've got x minus 3i, okay, x plus 3i, and then x squared plus 7x plus 10, I believe it was. Now, I can factor this a little further. Whoops. So here's x plus 2 and x plus 5. Yeah. So we know now what our zeros are. 3i, negative 2, and negative 5. Okay, so we want to find the solution intervals for these types of inequalities. In other words, inequalities that aren't linear. So here's the approach we take. We first of all find boundaries. We'll do this polynomial one first. We find boundaries, and we set this equal to 0. So if I set this equal to 0, so I've got x minus 1, x plus 1, x plus 4 equals 0. When we do that, we find solutions to this equation are 1, negative 1, and negative 4. In other words, that's where this polynomial is equal to 0. Now, what we want to do is find, well, where is it above 0? In other words, where is the graph above the axis? So what I'm going to do is I'm going to make a little number line, and I'll use that to divide, the whole number line into these regions. So we've got, this is 1, by the way. Okay. So I pick test values like -5 over here, -2 here. Between -1 and 1, I pick 0, and anything bigger than 1, I'll just pick 2. Now I'm going to test those values. So here I go. Now let me give myself a little more room down here. I'm going to move this thing down a little bit. Whoops. Move it down a little bit. Okay. Now let's see what I've got here. I've got X, and I've got X plus 5. I mean X plus 4. X plus 1, and X minus 1. And I'm going to test -5, -2, 0, and 2. Now, I don't really care about the values. I just want to know, do I get positives or negatives? So here's what I'm going to do. I'm going to plug in the -5. And if I do, I get a negative for this first factor, a negative for the second, and a negative for the third. That's 3 negatives. So the polynomial is below the axis for everything less than -4. Now I plug in a -2. The first factor, I get a positive. The second factor, a negative. And the third factor, a negative. 2 negatives make a positive. Now I plug in a 0, and I get a positive, and a negative, which gives me a negative. So it's below the axis there. Now if I plug in a 2, I get positive straight across. See, all 3 of these are positive. Now we wanted to know where this polynomial was greater than or equal to 0. Well, from -4 to -1, unioned with 1 to infinity. And notice I have the little braces here to include the endpoints because it was greater than or equal to. Okay, now let's look at this one. What we want to do on this one is find the boundary numbers as well. And I'm going to do this in 2 parts. I'm going to set the numerator equal to 0 and find the zeros of the numerator. So I get x plus 6, x plus 2, and I get x equals -6, x equals -2. Now, I also want to find out, I want to find the zeros of the denominator. And that gives me x equals 5. But I'm careful with this one because when I present my solution, I don't want my solution to include 5. Even though it's less than or equal to, I'm not going to include that 5. So make a little number line here. And I've got -2, I've got -6, and I've got 5. I'm going to circle 5 so I don't forget. And then what I want to do is I want to pick test values. So I'm going to pick a -7, a -3, a 0, and a 6. I'll pick those numbers to test. So here's what I have. And I'm going to look at the factored form. I've got x plus 6, x plus 2, all over x minus 5. And I'm going to put in a -7, a -3. Give myself some more room here. A -3, and a 0 and a 6. Okay. Now, if I put in a -7, notice the top, I'm going to get a negative, and the bottom a negative. So I get 3 negatives, that gives me a negative. So it's negative over here in this region. Now, if I put in a -3, up top I get a positive, a negative, and on the bottom, a negative. That gives me a positive. So I get a positive between -6 and -2. Now, if I put in a 0, I get a positive, and a negative. That gives me a negative, so it's negative over here. And then if I put in a 6, well, heck, I get positives all across. The first factor is positive, the second factor is positive, and the third, so that's positive. So we're ready then to write our solution region. Remember, we were looking for when it's less than or equal to. So here I go. It's going to be -infinity to -6. And notice it's inclusive, right? Okay, so that's this region. And then union with -2 to 5. But 5 I can't include, so I have to do that. So that's our solution region. These are the intervals where this function is below the axis. Okay, let me look at this first one here. First of all, the y-intercepts, we find those the same way as with the rational functions as we do with the others. We want to find the y-intercept by letting x be 0. And when we do that, we get 0 for x and -5/4 for the y. See? So all I did was replace the x with 0. Now to get the x-intercept, we're going to set the numerator equal to 0. And we get x equals 5. Okay. Now really, you're setting the whole function equal to 0. You're setting f of x equal to 0 and solving, but the very first step in solving that would be to multiply by the denominator. You would just clear out the x plus 4. So you're finding, by you're just taking a shortcut, x minus 5 equals 0. What makes the numerator 0 makes the whole thing 0. Now, as far as the vertical asymptote, you set the bottom equal to 0. There's your vertical asymptote. Okay. Now we've got the horizontal asymptote. With the horizontal asymptote, remember you have these cases. If the degree on the top and the bottom are the same, which they are here, for x to the first over x to the first, the horizontal asymptote is the ratio of the leading coefficients. So it's 1 over 1. And that's what it asks us to find. The y-intercept, the x-intercept, and the asymptotes. And the two asymptotes are the vertical asymptote and the horizontal asymptote. Now this one down here, same way. We work this problem exactly the same way, except there's going to be some differences here when it comes to finding the horizontal asymptote, because the degree on the top is bigger than the degree of the bottom. Let me make a change here to this one. Let me make this a 10x and this a 9x. Yeah. So x squared plus 10x plus 9. Yeah, that one. That's what I intend. Okay, so here we go. We know these. So you look at this and you remember, you try to break it down just components of what I need to do. Need to find the y-intercept. Well, how do I do that? I let x be 0. So if you let x be 0, you get 0, 9 over 2. Everything goes away except the 9 up top and the 2 on the bottom. So that's the y-intercept. Now the x-intercept, we set the top equal to 0. And I wanted to make this, something that would factor nicely. That's why I changed it. So you want to find out the x-intercept, so you set the top equal to 0, and you get x plus 9, x plus 1. Now, if we did have something that didn't factor, that would be fine. We could use the quadratic formula on it. But okay, so we get two intercepts then. We get -9, 0, and we get -1, 0. because we've got roots there, -9 and -1. Okay, so those are X-intercepts. Now, for the vertical asymptote, we set the bottom equal to 0, and we get x equals -2. So there's a vertical line right through the x-axis at -2. Now, at this point, we're looking for the next asymptote. It's either horizontal or slant. And because the degree on the top is bigger than the degree of the bottom, we know it's not going to be horizontal. It's going to be a non-horizontal asymptote. So what I'm going to do is I'm going to divide. And the idea here is, well, I'll show you. After we divide, I'll show you what's going on. So we have x plus 2 into this x squared plus 10x plus 9. So x into x squared will go x. Then we multiply. Now x will go into 8x plus 9, 8. And then we subtract and we get a -7. Now, here's what we have. Let's think about what we have here. We have x squared plus 10x plus 9 all over x plus 2 equals, let's see what it equals. It equals x plus 8 plus -7 over x plus 2, right? That's what we found out with our division. Now, when we talk about horizontal asymptotes or non-horizontal, the slant asymptotes, what we're talking about is what does the function do for very large values for x in the positive direction or in the negative direction? In other words, as x gets larger and larger and larger, what does this thing right here look like? Well, it's this. This is exactly this. These two are the same. But for very large values for x, we can see that this thing right here just goes to 0, right? Think about it. You've got -7 divided by this increasingly large number down here. A billion, a trillion, right? 10 trillion. Okay. So poor little -7, it's just dividing by bigger and bigger numbers. It's going to 0. So really, as x goes to infinity, all that matters is this thing, x plus 8. X plus 8 plus this little dust in the scales over here. So we say that y equals x plus 8. That's our slant asymptote. Okay, that's our slant. We don't put the remainder in there because that remainder is just going to go away. And we're looking for what happens for these large